Hello everybody. I guess some of you are kind of getting back into the kind of the work mindset, had a few days off. It does say in the chat I've just seen that a few people aren't necessarily fully locked in, or they haven't been so far, but we've got plenty of time. It is Friday today. You've got loads of time tomorrow and all of Sunday, and then your exams Monday, and then it's just like maths, all the other subjects all kind of come at once. But I hope all of you are doing really well. We're going to be doing an AQA paper today. So this is based on a PMT predicted paper that they've put up for free on PMT. So the actual stuff I'm going to be going through, it's completely free for you to download. You just need to go to the PMT website. I'm not affiliated to them. I'm not doing it because this is paid partnership. It's just basically a load of questions that I can go through. And on YouTube, I can't show real AQA questions. But of course, these are going to be very similar to the kind of topics that are coming up in paper 2. Now, as always with these videos, this is not, I don't think, an accurate prediction of exactly what's going to come up, but you've seen that already that if you did the AQA predicted paper 1 from PMT, the same questions didn't come up in the exam, but of course it's the kind of the normal topics that you need to know about, and it's really about the approach to all of these questions. So yeah, hope all of you are doing really well. Yeah, here we go. Somebody's asking in the chat. Basically, if you are doing OCR, if you're doing Edexcel, this can still be useful because it's a lot of the same physics, but obviously really this is specific to AQA students. Talking of which, on Sunday I'm going to be doing a mega last minute masterclass. It's a couple of hours going from 1:30 till 3:30 in the afternoon. So if you want to book onto that, all you need to do is go to my website, which is alevelphysicsonline.com, look on the classes page, and then you can book onto that masterclass this coming Sunday. There's a code just underneath me down here for 10% off, but basically it's £30 for 2 hours, and there's a bit of time after that masterclass to kind of go and put this stuff into practice, and hopefully that's going to help you feel really prepared for paper 2. And it's been amazing. If anybody who is in my first masterclass, if you're in the chat at the moment, do come and say hello, and obviously do let me know if you're going to be back again booking for that second one. Somebody says, would the masterclass be worth it if you know nothing? Yeah, definitely. If you know nothing, definitely come to the masterclass, and what I'll do is go over like some of the key points, the things that I've seen are kind of common mistakes and errors that students find, and we'll kind of cover those in that thing. Also, tomorrow morning I'm going to be doing a free masterclass all about capacitors. That's at 10:30 in the morning. It's completely free to attend, provided you use the code capacitor20. So what I'll do, in the chat in the live stream at the moment, if you put in the code capacitor20 at checkout, that means you basically get an hour-long capacitor masterclass. We'll go through this topic. We're going to do some of that today as well in this session coming up. But if you want to come along tomorrow morning, that's a completely free masterclass from 10:30 till 11:30. Right. Should we just get started? Okay, so this might be a mega thing. Maybe it might be a couple of hours, maybe a bit longer. PMT Education, they've got this predicted paper free to download. It's based on paper 2 topics. We've got the author there, and here we have a question. So I suspect a lot of you might have seen the paper already or had a go at it, but of course I'll go through the question and go through my approach. I must say that I haven't practiced this, so fingers crossed I know what the answers are, and I can sort of just work through it sort of stage by stage. So fingers crossed there won't be any big mistakes. Hello to Joseph. Paper 1 went really well, and thanks as well that hopefully something I said has helped for that. So yeah, it's great that so many people have found my material useful as they've prepared. Right, let's start with blue. So calculate the total energy transferred from the person's body to the water for both heating and evaporating. So every time you get something like this, it is always worth just double checking with your data and formula booklet. I've kind of added notes to this as I've been working through past papers for the last few weeks and my other things. And basically these are just like extra bits and pieces I've added, like extra useful equations which might be useful. For this one we're going to be using these two here, basically saying that Q is equal to MC delta theta and Q is equal to ML. Now, this is all revision, so hopefully this isn't stuff that's completely brand new. But Q here represents the thermal energy. You've got the change in temperature, so this one is about something changing temperature when it's in the same state. And this is where we have something where we've got a phase change going from maybe solid to a liquid or a liquid to a gas. And if it's vaporization, LV, that's going to be as something goes from a liquid to a gas. So the total thermal energy transfer, Q, is going to be equal to mc delta theta plus mLV, or Q is equal to m times c delta theta plus LV. Okay, so I think that's probably the simplest way to work this out. Now in the question, we've got 0.25 kilograms of water. So Q then is going to be equal to 0.25 times the specific heat capacity of water, and it's going to raise the water temperature from 28 to 35. So that's changing by 7 degrees. And then we're going to add that to the latent heat of vaporization, so that's 2.3 times 10 to the 6. Okay, so we've made sure that everything is in like joules and kilograms, all these kind of standard things. So if we just put the numbers in, this gives me a number equal to 582,350. And I guess, to give my final answer here, this would be 5.8 times 10 to the 5 joules. Now, looking at this, I think this is a bit different to most questions, because most questions tend to look at maybe the latent heat of vaporization is when something is maybe at its boiling point, so it might be 100 degrees. Here they were talking about evaporation, and of course evaporation will happen below the boiling point, which is why water can turn from a liquid into a gas even at room temperature. So this is why things like a puddle on the floor will evaporate over the day, or people will sweat even though they're not at 100 degrees, that water's still changing from one state into another. So yeah, basically that one there. I've given my final answer to two significant figures over here, just like the raw data is given to two significant figures as well. And I guess, yeah, there we go. All good? Everybody doing this all right? Okay, the next one. Jeremiah instead chooses to dry off by staying in the sun. Explain how factoring in the sun's thermal radiation may change how they perceive the sensation of staying cool after the swim compared to Sarah. Consider how it affects the actual energy loss from their internal body stores. I reckon this is probably worth more than 2 marks. And also, yeah, people are saying here, I feel like these predicted papers are easier than they should be. Yeah, I think a lot of the questions are relatively straightforward. But again, don't treat this as a prediction of what's going to come up. Just treat it as another set of questions that allow you to like just practice stuff. And of course, I would only be doing the predicted paper if I were you, having done all of the other past papers that you can find on A-Level Physics Online or on the AQA website. So ideally, you've done like the 2025, 2024, 23, 22, 20, all the way going back to like 2017. And when you've done all of those real past papers, that's when, if you need some more example questions to kind of just remind you about how much you know, that's when it's time to do this one. So, sorry, one sec. Okay, so what can we say? So basically, how does factoring in the sun's thermal radiation change how they perceive the sensation of staying cool? I would say that if you think about a person, so here's Sarah and here's Jeremiah. What they both have on them is water, and of course that water is going to be evaporating, and as it does so, the fastest particles are going to be the ones that gain enough energy first to escape. And that means whatever's left is going to be cooler than it was before. And that's why evaporation means that, or that's why we sweat in the first place, so that we have this evaporation, which is basically taking that heat energy away from us. Now, all of this evaporation from Sarah occurs because of her thermal energy, or her internal energy store being transferred to the thermal energy of these things. With Jeremiah, we also have energy coming in from the sun, and then we've got the evaporation happening. So what that means is the energy needed to evaporate the water, which we worked out in the last question, is about 5.8 times 10 to the 5 joules. All of that energy is going to be coming from Sarah's internal energy store. We need the same amount of energy to evaporate the water from Jeremiah, but actually some of that energy is going to be coming from their stores and some of it's going to be coming from the sun. So basically that's how much energy Sarah loses, whereas the energy that Jeremiah loses is going to be smaller than this number, because some of that energy is going to be supplied by the energy coming from the sun, and that means they feel that they're warmer, whereas Sarah will feel colder. Now what I'm not going to do here is basically explain everything and kind of write out a full answer. I think, if you really want to see the full answer, they do have model answers on PMT. I just thought I'd explain my reasoning as I just talk around the answer to some of these questions. Is that making sense so far? Cool. Right. Okay, so the next one is about popcorn. So basically what it's saying is a popcorn kernel is a highly sealed seed. So basically that's the popcorn. Inside it, it's got some water which is going to turn into a superheated steam, which is like an ideal gas. So that's basically just a thermal physics question. And then we've got the volume of whatever it is, and then pressure builds up until the hull ruptures violently in a pop, which is 180 degrees. Given that the molar mass of water is 18 grams per mole, determine the pressure inside the kernel at the point of rupture. So there's quite a lot going on in this question. I would say that anytime we've got something like an ideal gas, there are loads of equations that we might be using. And so again, it's just worth looking in the data sheet, thinking about which of these might be useful. So first of all, we've got the normal gas laws. So PV equals nRT. So I'm going to write down PV is equal to nRT. That one could be useful because we've got information here about the temperature. We've got information about the pressure. We've got the mass of something. And I guess what we need to look at is the pressure inside the kernel at the point of rupture. So that means the pressure is going to be equal to nRT over V. Okay, so we know the volume, we've got the temperature, we know R, but what we don't have is the number of moles. But what we do have is we've got the mass of something, and you might remember that the number of moles is equal to the mass divided by the molar mass. Okay, so that's going to be equal to the mass that we have, which is 1.5 times 10 to the minus 5 kilograms. We're going to divide that by the molar mass of water. Now that's 18 grams per mole, and therefore that's going to be 0.018 kilograms per mole. So I've made sure that I've got these in standard SI units. Now, for those of you doing chemistry, by the way, in the chat, do let me know, do you do A-level chemistry as well as A-level physics? So what I'll be doing is, as we go through this, I'll be trying to keep an eye on the chat as much as possible. There'll definitely be a bit more interaction when we do the multiple choice questions, but if you have questions about what I'm doing or any questions about A-level physics, do ask away and I'll do my best to answer them. So anybody else there doing chemistry? Well, what I remember from doing lots of GCSE chemistry recently is that often in chemistry you talk about things in grams, so we've got the molar mass in grams, but if you're giving a mass in kilograms, just make sure that we've got the same units for both. Okay, so N is equal to M over M, so we can therefore say that the pressure is equal to M over M times RT over V. We'll then put these in, so that's equal to 1.4 times 10 to the minus 5 divided by 0.018 times by 8.31, and then we're going to multiply that by the temperature, which is given here in degrees Celsius. And I think it's worth, if you do have a highlighter, get your highlighter out every time you see a temperature and just highlight it, and that shall hopefully remind you to check if you've got the temperature there in either Kelvin or degrees Celsius. Okay, how's that going? Right, sorry, I've lost my bit on here. Okay, so we're going to add 180 to 273, and then we're going to divide that by the volume, which is 1.0 times 10 to the minus 7. Okay, and by the way, if I am making mistakes as I'm going through this, then do let me know if I've messed anything up. Okay, right. So I'm getting a pressure here of 29278900. So that's 2.9 times 10 to the 7. Is that right? Do let me know. The chat's kind of slowed down a bit at the moment, so do let me know if I make any mistakes. So that one there I thought was fairly standard. Again, anytime you get an equation, double check everything in your data book, including the constants. So I used 8.31 as the molar gas constant, but just always double check, just in case you've written down the wrong number, like 8.13 or whatever it might be. Always keep an eye on just writing down the correct equation, double checking it, just in case you've made a silly mistake, and especially when you're adding in these kind of physical constants. Okay, in an experiment, a student, here we go, for some reason my chat isn't loading as much as it needs to. Oh yeah, by the way, thanks for all of the likes and the hearts and the smiley faces and everything. And if you haven't already done so, can you make sure that you like the video, and also afterwards do share it to people in your class. If they're not here this afternoon, I don't know what else they'd be doing, but if you haven't already done so, do share the content I've got. There's loads of stuff on my website that's going to help you and everybody else for paper 2 and also paper 3 next week. Okay, in an experiment, a student measures the mass of the kernel before and after it pops. Describe and explain the expected change, if any, to the mass. So I would say the mass decreases. So that's basically the kind of the first point. And I guess, of course, this is because because what we've got here is a small amount of trapped water, and that water is basically going to go from being trapped within it, and then it's going to end up as steam. And I guess that's why when you open a bag of popcorn, if it's just been in the microwave, that steam escapes from it. That's because the water in the kernel evaporates. I think that's pretty much all we need to know, isn't it? Cool, thank you to Rufus here, who'll be sharing this far and wide. Good stuff, Rufus. Okay, right. The next question says, the actual pressure at which the hull ruptures is closer to 9.3 times 10 to the 5, rather than the answer that we got previously. I'm just going to put this above it, was 2.9 times 10 to the 7. So that's the answer that we worked out. That's the answer it gives us. Suggest 2 reasons as to why the pressure is much higher than the actual rupture pressure. So what do you reckon the reasons could be? And also, how does this link to the ideal gas assumptions? Well, I guess what we need to think about then is, what are the assumptions for the for an ideal gas? And I think this is where the word negligible is super important. So in the chat, what would you reckon the assumptions about the ideal model of an ideal gas that we can use that aren't maybe relevant in this case? So basically, I would say that in an ideal gas, what you have are the volume is negligible. Junior Marcus, the volume of what though? Is it the volume of the particles or what else? Negligible volume? Yeah. So basically, what we assume is in an ideal gas, the volume of the particles or the molecules is negligible compared to the size of the container. But of course, if you've got a kernel, which is a lot smaller, and we don't have something which is acting purely as a gas initially, that's going to be much more in the liquid state. So therefore I say that the volume of the particles isn't negligible. So the volume of, so lots of people here saying that top one there. So basically, we could say that the volume of the molecules is not negligible. I think that's a good one to start with. Right, what else can we say? I guess ideal gas assumptions. I guess we've got the time between collisions, but we don't really know much about that here. We've got the perfectly elastic collisions. I don't know. I don't know the time between collisions. Yeah, I don't know. It might be that basically, I don't think there's another good ideal gas assumption that we can use to answer this equation or this question, because I don't think any other answers are to do with the assumptions that we use for an ideal gas. So I'm not sure about the next one. And I don't necessarily think, maybe the temperature wasn't constant, but you see the temperature not being constant isn't based on the ideal gas assumptions. So I think that is a true thing that might not be constant, but I don't think that answers this question they've asked. The mark scheme says estimates the number of moles. Possibly, but I don't see why that's one of the assumptions for an ideal gas. Let's just ignore that. Let's just move on. Right. Derive an expression for moons in a circular orbit to show that t squared is proportional to r cubed. So this one here is a standard physics question that you can do. I reckon that last question, the mark scheme maybe isn't as good as it could be possibly. Not all the water might have evaporated into a gas. But that doesn't then relate to the ideal gas like you say, Anna. Great point. I'm not sure the second one. Right, this one here, you should be able to do in under 1 minute. Okay, so should we see if I can do that? So basically, we know that between these two things, there's going to be a size of the force between them, which is equal to gmm over r squared. And that force causes this centripetal force, which is equal to mv squared over r. So if we equate the two things together, gmm over r squared is equal to mv squared over r. That cancels with that cancels with that. So gm over r is equal to v squared, but of course v is equal to 2 pi r over t. So v squared is equal to 4 pi squared r squared over t squared. Put this into that. So gm over r is equal to 4 pi squared r squared over t squared. We bring this up to say that t squared is equal to 4 pi squared r cubed over gm. Okay, so basically that's what you should be able to do in under 1 minute. And therefore, that is 2 easy marks. This has come up in previous past papers. I've seen it in variations in OCR, Edexcel and AQA. So it's just something you need to know. So the force due to gravitational attraction between them provides a centripetal force. We equate the two things together, do some cancelling. Because we've got this circular orbit, we know the speed of that orbit is equal to 2 pi r, the distance it travels around that circumference in the time period t. We put that back into there, bring the t squared up, bring the r over to the r squared to make r cubed, and then we've got this. So this thing here is what all of you need to know about. And if you can't do it, you need to keep doing it repetitively for the next 2 days. Store it in your short-term memory. and then you can forget it for the rest of your lives. Okay, let's keep going. This one is again a lovely question. Yeah, that was just a Kepler's law derivation, perfect. So this one here, we've got blah, 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 all that good stuff. Use the expression derived to show that the theoretical gradient of this line should be 1.5. So we said that t squared is equal to 4 pi squared over gm times r cubed. Okay, now effectively what we can do is we can take logs of both sides of this equation. And I guess to kind of keep it simple, this thing here is basically a constant, because you've got the big G universal gravitational constant, and we've got the mass of that planet. So I guess that means t squared is equal to kr cubed, to keep it simple. And if we take the log to the base 10, which is what we've got here, that means 2 log t is equal to log k plus 3 log r. Okay, so I've taken logs of both sides. And what we've got is plotted on the y-axis. I'll just zoom out slightly. Plotted on the y-axis, we've got log t. So if I divide both sides by 2, we can say that log t is equal to, I'm just going to put this over here to say that's equal to 3 over 2 log r plus log k over 2. And then the top tip really is we say y is equal to mx plus c. So at some point in your exam, my prediction is you should write that down. And this then allows us to identify what all of these things are. Now on the y-axis we've got log t, and on the x-axis we've got log r. So that means the gradient is equal to 3 over 2. And therefore m, the gradient, is equal to 3 over 2, which is 1.5. And so this is like a fairly standard question. I've got like an almost identical question, I think, in one of my daily workout books, looking at data actually for the same moons. And I basically, if you plot the data, we then get log t, log r, and this then shows that we've got that t squared and r cubed relationship. Yeah. Yeah, so user EP7LU9DS50A says, when taking logs, do you always bring the number that was on the power before the letter? Yes, you do, yeah. So this basically means that if you've got log of t squared, well, t squared, the log of that is going to be 2 log t. And that one there would be 3 log r. So that's just one of these log laws that you should be familiar with. But I reckon if you're not sure, this is going to be the kind of example where they might ask about it. Okay, so here we've got information about Jupiter's 4 largest moons. Use this data to determine the mass m of Jupiter. So how can we do that? We know, let me just write down the equation one more time. So this is what we said previously. T squared is equal to 4 pi squared over gm times r cubed. And that then means that m is going to be equal to 4 pi squared over g times r cubed over t squared. Is that right? I think that's all good, isn't it? So what that then means is if we know the average value of r cubed over t squared, so basically we've got lots of data here. Now the best way to do this would be actually to plot a graph of this to then use the gradient to find the value of m. But I guess what you could do here is you could just work out r cubed over t squared, and then you just multiply the average of those values by 4 pi squared over g, which I reckon is easy to do, but it's quite time consuming. So my approach for this would be, well, let's just do a column over here, and I know you shouldn't write out. So in a real exam, don't write outside the paper, but they'd also kind of design the paper to allow space for this. Let's look at r cubed over t squared. Okay, so the first one we've got 4.22 times 10, 4.22 times 10 to the 8, cube that, and we're going to divide that by 1.53 times 10 to the 5 squared, and that's equal to 3.21 times 10 to the 15. And of course these are all 10 to the 5s, or yeah, so we should find that this number should be the same. So the next one, I'm just going to do 6.71 cubed divided by 3.07 squared, and that's going to be 3.205, so that's the same, times 10 to the 15. The next one, we've got 1.07, which is cubed, divided by 6.18. Oh, sorry. That's going to be 3.21 times 10 to the 15, and the last one is going to be 1.88 cubed divided by 1.44 squared, which is going to be 3.20 times 10 to the 15. So I guess looking at all of this, the average value for that, I'm going to say, is 3.21 times 10 to the 15. So the mass then is equal to 4 pi squared divided by 6.67 times 10 to the minus 11 times 3.21 times 10 to the 15. Is that all right? Yeah. This gives me an answer equal to 1.90 by 10 to the 27 kilograms. Okay, yeah, I would say don't be sharing your email in the chat on the live stream just in case. I'm afraid the 2025 mark scheme is still kind of out of bounds for students. Your teachers will have it at school. So it might be worth, if you're looking for the 2025 mark scheme, email your teachers. They will probably be checking their emails at some point this weekend, definitely before they go back into school on Monday, and they can send that across to you. Okay, is that right? I think that's the right answer. And I guess if this is the mass of Jupiter, it's going to be bigger than the mass of Earth, which is 10 to the 24, and smaller than the mass of the Sun, which is 10 to the 30. So we know it's about the right one. Okay. Why is gravitational potential always negative? So I think this is like quite a nice kind of sort of standard question that often comes up. And basically, because what you need to be doing is adding energy to the system, or the energy per unit mass, as you increase its distance away from an object, until at infinity that attraction, the gravitational potential at that point is going to be zero. So that's why the gravitational potential is always negative, because what you're having to do is we are doing work against an attractive force, and that's work per unit mass for gravitational potential. So yeah, basically, let me just write that out. Yeah, I guess work is done per unit mass to move a point in, to move from a point in a gravitational field to infinity, where the potential is then zero. Okay, so basically we add stuff until something gets to zero, and therefore whatever we had before must be negative if you can add something positive to something negative until it's zero. Does that make sense? Yeah, so 0 to infinity, gravity is attractive, so work done to separate. Perfect. Cool. Okay, Callisto has a radius of 2.4 times 10 to the 6. Determine the escape velocity from its surface. So a lot of this is actually pretty straightforward if you can remember the equation for escape velocity. So, have I got this in my data book here? So what I've got is, yeah, so basically V is equal to the square root of 2gm over r. Okay, now this is an equation that you need to know how to derive. Have I done that? Yeah, so basically root 2gm over r. So I think that all of you now need to take a picture or a screenshot or like a mental kind of snapshot of what this is. This is going to be the escape velocity of something, and if you know it, then this question becomes super easy, because if you know that, you've basically got the radius, you've got Callisto, I think it says here. Does it give you the mass of it? Yeah, it's got the mass of it over here in that part of the question, and then you just put the numbers in and you get an answer. If you need to know how to derive it, I guess what you've got to think about is there's going to be some kinetic energy, which is equal to a half mv squared, and this kinetic energy has to be enough to be equal to the gravitational potential energy for it to escape. And that's going to be equal to gmm over r. Okay, so basically that's the kinetic energy, that's the gravitational potential energy. And you can see that we've got a small m that cancels with that. And then we bring the 2 up here. So v squared is equal to 2gm over r. And then, of course, v is just going to be the square root of 2gm over r. So we're basically saying, do we have enough kinetic energy to overcome that gravitational force of attraction? Yeah, so it's the escape velocity when the gravitational potential energy is equal in size to the kinetic energy. And of course, if this is bigger than that, that's when something can escape. So really, ideally, v wants to be bigger than or equal to this. So if we put the numbers in, v is going to be equal to the square root of 2 times 6.67 times 10 to the minus 11, multiplied by the mass, which was given to us in the previous part of the question as 1.08 times 10 to the 23, divided by the radius of 2.4 times 10 to the 6. Excuse me 1 minute. By the way, do let me know if I'm making mistakes with my calculations, because it's great to have, I think, about 60 people in the chat at the moment. I know lots of you aren't saying anything because it's just me just explaining physics, but if I do make mistakes, do let me know, because it's difficult to talk and do calculations at the same time. The escape velocity here would be 2450, so I'm going to say that's 2.5 times 10 to the 3 meters per second. I think 2 significant figures is appropriate because we've got 2 significant figures up there. Yeah, is that all right so far? So basically 2 significant figures here, 2 significant figures over there. So 2450.1 is going to be 2.5 times 10 to the 3. Cool, thank you NH, doing perfect so far. Oh my gosh, my back is absolutely killing. I think basically I spent about 3 hours doing a live stream yesterday, and I'm sat on, actually I haven't shown this to you. Do you want to see the best science stool everywhere? So these I got from a skip at school. Check these out. Look at that. So I've got my padded top to a science stool, and the whole thing has been painted in a galaxy paintwork. So you can see the stars on the galaxy there. So it is better than a normal science stool, but I know if you've been in a lesson at school, doing like an hour sat on the science stools isn't the most comfortable. Right, cushioned as well. Yeah, by the way, these ones here, they were in the skip because the top had just been like kicked off and broken by horrible children. So basically there wasn't a top, so I got a piece of wood. I put some foam on top of that and this kind of like fake leather stuff that's stapled on the bottom. Yeah, so it's good. Why don't I get a normal chair? Oh, the reason I'm not getting a normal chair is because basically the bench I'm on is higher than a normal desk. So if I was to sit in my normal chair, I would be kind of like at this level. And I think that would be a bit weird for the videos. Yeah. Okay, right. A side hustle in upholstery. Maybe. Right. So 1 sec. Let's go back to the next question. Also, it's not wine, it's Vimto. I had a bit of a discussion yesterday in my stream. What is your favourite? So when you're saying like the peach monster, I suspect that's not good for your health or your future lifespan or health span. So yeah. Are you Ribena? Are you Vimto? Let me know in the chat what is your favourite thing. Pepsi Max? Yeah, I know water's probably best, but that's boring, isn't it? Okay. So we've got tank, we've got a pump, charging nozzle, deflecting electrodes, paper. So I guess this one here, looking at this is about the motion of charged objects in an electric field. Dr. Pepper cream soda. Oh, that sounds good. That sounds good. Right. Okay, so this one here, in the words of the Lego person, start with a diagram. If you do this, then that just means you're much less likely to make mistakes. So basically, start with a diagram. Even though there's a kind of sort of schematic on the previous page, if you do a diagram, everything is going to be so much easier. So here is my diagram. A couple of charge plates. So basically, these are 1.2 centimeters long. So that's going to be 0.012 meters. So that's the length of the plates. We'll assume that something comes in, and then basically what it's going to do, it's going to go away from that center line, and it's going to deflect up by 3.5 millimeters. That's 3.5 times 10 to the minus 3 meters. So that's going to be the deflection upwards. We've got a charge and the mass of it. The horizontal velocity is 18 meters per second, so 18.0 meters per second. Yeah, determine the required potential difference across the deflector plates to achieve this. So let's imagine that that's at 0 volts and this is at some unknown voltage V. Okay, so this one here seems to be, somebody says they love me. I love everybody back, thank you. Right, somebody thinks it's going to be in the 10 to the 7 range. Okay, so what's the PD across the deflector plate to achieve this? So, a few things here. We're going to have some kind of suvat, I guess, because what we're going to have is we're going to have a parabolic path of that particle, because as it's going through between the plates, the force is always going to be in that same direction. And yeah, so basically there's going to be some kind of suvat thing in that kind of direction. So what do we need to know? I guess thinking about like the vertical direction first of all, I'm just going to write down suvat, and then we can start to write down what we know. So in the vertical direction, the vertical displacement is 3.5 times 10 to the minus 3 meters. The initial velocity is 0 meters per second, and we don't know how long it's there for, and we don't know the acceleration or its final velocity. So far, that's not so good. But what we do know is we can work out the time that it's in that field for. So in the horizontal direction, we can say that its speed is equal to its displacement over time, or its velocity is s over t. So in the horizontal direction, the time it takes is going to be equal to s over v, and it goes 0.012 meters at a velocity of 18.0 meters per second. So we can work out the time, which is 6.67 times 10 to the minus 4. Yes, I said it. And therefore we can put the time down here, so that's 6.666 recurring times 10 to the minus 4 seconds. Okay, so we need to therefore know. Okay, I guess that then means we can work out the acceleration, because if we know the acceleration, that's going to tell us, I guess, from F equals ma, if you know the acceleration, we can work out the force. And if we know the force, we can then use that to work out the electric field and therefore the V over D. Okay, so, right. Yes. Right, have I started something in the chat? Everybody's saying it. Yeah, so basically, let's work out A. So we're going to use the one that doesn't have V. So that's basically S is equal to UT plus a half AT squared. That's always 0, so handily. And A is going to be equal to 2S over T squared. So that's 2 times 3.5 times 10 to the minus 3 over 6.67 times 10 to the minus 4 squared. So I'm going to keep my answer there, square that, and then we've got 7 times 10 to the minus 3 divided by that is, the acceleration is 1.575 times 10 to the 4 meters per second. Yeah, oh yeah, by the way, if everybody could like the video now, that would be amazing. So Amari says we're at 25 likes at the moment. Is that it? So that's basically 1 like every 2 minutes. That's depressing, isn't it? Oh, thanks. By the way, thank you for all the love coming in the chat. Thank you so much. Right, so we've got the acceleration. That means the force applied is equal to the mass times the acceleration. And it says the mass of the droplet is 1.1 times 10 to the minus 10 times that previous answer. Which is then 1.7325 times 10 to the minus 6 newtons. And then, of course, we can say that the electric field strength is going to be equal to the force per unit charge, and that's equal to V over D. Is that right? Have I done that? Is that the right thing we need? Do we know? Do we know? Oh, here we go. It says on the previous bit over here that the plates are 10 millimeters apart. So that's good. So basically, what we can then say is, because the electric field is F over Q, the force per unit charge, and that's equal to V over D, V is going to be equal to FD over Q. So it's that previous value here of 1.7 times 10 to the minus 6 multiplied by 0.010. So that's the distance between the plates, divided by the charge on them, which is 2.4 times 10 to the minus 14. And this gives me an answer equal to 7.2 times 10 to the 5. And that would be volts. Is that right? 7.22 times, yeah, I think that's right. Yes, we got you. Okay, how many likes do we have at the moment? I can't quite see on my thing how many people actually like this. I guess if you don't like it, then you don't have to watch. Right, is that the right answer? Yeah, I think that's right. Cool. Right, the next question then. So this one here, I think, is a standard question. Still 25 likes. I'm sure once it's been up for a couple of days, it should get more than that. So this one here, I think, is a very standard question. There's a lot of work. I would say that's probably more than 4 minutes worth of work in the exam. But basically, draw the diagram to start with. Write down SUVAT, identify what you know and what you don't know. Then work out the bits that you don't know. And then you use that, if you know the force, you can say that these two equations, F over Q is equal to V over D. You put it in, and then you get that answer. Cool. 46, 43, cool. Okay, this one here, okay, it's a nice 2 marker. So, inside the nozzle, the ink droplets are accelerated by a separate electric field. Calculate the accelerating PD to give the droplets this velocity. So basically, the charge on the droplet times the potential difference through which it's accelerated That's basically the energy transferred to that droplet, and that's going to end up as the kinetic energy of that thing. And I've been very careful to use a big V, I'm going to call it ACC, and a little v for the velocity. So that means the accelerating potential difference is equal to mv squared over 2q. So that's the mass of 1.1 times 10 to the, what was it previously? 10 to the minus 10 times 18 squared over 2 times 2.4 times 10 to the minus 14. I think that's the right numbers. Okay. Yeah, by the way, the recording says, Enki says, the recording will be uploaded as usual afterwards. Yeah, so basically anything on YouTube I do live, I'll just keep it there. So it'll sit there basically between today and tomorrow and Sunday. And then I guess after that, nobody's going to watch it again, are they? It might be there next year. Who knows? So basically, yeah, I'll leave the recording up on YouTube. So if there's anything you've missed, you can go back and rewatch it if you need to. So this is 7.4 times 10 to the 5. I think that's right, isn't it? Yeah, that looks good to me. Cool. The manufacturer considers doubling the velocity of the ink droplets to speed up the printing process while maintaining plate length and potential difference across it. How does that affect the time spent by the ink droplet in the field and the vertical deflection? So, if you had, well, we can see from the first thing over here, I guess this goes back to that previous question. So if you've got something where, if you had something where it was going at twice the velocity, then the time it spends in the field goes down by 2. So basically, this is what we worked out previously. If you had 2 times the velocity, then that would mean you're taking whatever distance it travels through, and it's going to double the velocity, so it's going to half the time, so that makes t over 2. And if you've got half the time over here, so that's now t over 2, what effect does this have? Well, the acceleration is now going to be 2s over t squared, so we're now going to have the acceleration going down by a factor of 4. And that would then mean that in the vertical direction, if it's got we'd have the same acceleration, sorry, so basically 2s is equal to at squared. But I guess if you've got the same size acceleration, then that would mean that s is proportional to t squared, but, sorry, so you'd have the same size acceleration. The displacement then is going to be proportional to t squared, but if t's gone down to a half of its original value, then s is now going to be the original value divided by 4. So I guess what we can say here is that basically time in field is equal to half, and that means vertical displacement is equal to a quarter of original value. Okay, and I guess when you'd explain it, we can basically say that the time is equal to s over v, and of course the vertical displacement s is going to be equal to at squared over 2, and they're the equations that's coming from. Right. Okay, cool. Right, have we got to a nice number of likes yet? How many more do we need? Do we need to get, I'm not even going to say the number. Do I think, this is a great question, American, UK, do I think that paper 2 will be horrible because paper 1 was relatively easy? I don't think it's as simple as that. I think after lots of the criticism that AQA have had over the last few years, they've probably got a bit of a different kind of team and a different strategy for doing the papers. So if AQA paper 1 was good, there's no reason why paper 2 wouldn't be nice as well. So just because 1 was nice doesn't mean 2 is going to be bad. And likewise with OCR, they had like quite a difficult paper 1, so you know that means that probably, you know, it's very rare to get 2 really bad papers in a year. I think if paper 1 was fair, then I think paper 2 is going to be fair as well. Okay. Yeah, not that paper 1 was easy, but like I think paper 1 was like quite similar to past papers. It wasn't like noticeably different from what I've heard. Okay, on figure 4, sketch how the trajectory near the exit would differ from the ideal parabolic path and how that would affect the final position of the ink spot on the paper. So what we do normally is we assume when we're drawing the field lines that we've got this perfect uniform field in here. So if we think about what this looks like, I'm just going to use the width of my ruler to kind of just show that we've got this uniform field between the plates. Okay, and what we tend to do is we assume between the plates we've got a perfect field and there's nothing around it. The reality is that if you had a particle here, it would still be attracted to one of the plates. And so what we have is basically like an edge effect that maybe looks a bit like that. Okay, it's hard to tell exactly. And so with this edge effect, what that's going to do is it's going to keep the particle deflecting once it's left this region down here. So what we assumed previously was that as soon as the particle gets to this point, it then moves in a straight line. The reality is that when the particle has got to this point, there's still going to be a force acting on it, maybe here, and even when the particle is here, there's going to be a force acting on it. And that means the particle, and I should really be drawing this in pencil, but I'm just going to do it in pen to make it clear, it keeps bending and deflecting up until it kind of gets well away from the field, and once it's away from the field, it will then move in a straight line, and that means we're going to get a much bigger value of deflection than we had before. Okay, so that's what I reckon. So this one here, sketch the trajectory, so that's going to be probably 1 mark. So basically we can then just say how deflection is greater as a force still acts on it after it has initially left the plates. Okay, cool. Yeah, cool. Ben, yeah, hopefully it's been useful. Yeah, see everybody after the exams. Do you want me to do a video? I might just do a video on YouTube anyway, just say how did it all go, because I think they're quite popular and it's a good chance for people to like unwind and unload and I guess get ready for the next one. Okay, tomorrow I'm going to be doing a capacitor masterclass. All you need to do is book a place at alevelphysicsonline.com and use the code capacitor20, and basically that saves £20 on the £20 booking fee, and that's going to be basically Saturday morning at 10:30. So once this live is finished, I need to go and kind of prepare that. Yeah, right. Calculate the initial charge stored by the capacitor when it's fully charged. So we can again always just double check things in the booklet over here. Loads of different things here, but this is the one that we want. The capacitance C is equal to Q over V, and that means Q is equal to CV. So that's the charge stored is equal to the capacitance, which is 330 times 10 to the minus 6, multiplied by the potential difference of 12.0. And that's equal to 3.96 times 10 to the minus 3 coulombs. Easy, Q equals CV. Oh yeah, by the way, I did dilute it with water. I just had a bit of Vimto left in the bottle and I added water to it. So that's why I was pouring from the Vimto bottle into this. I'm not a psycho. I don't just drink pure Vimto. Although I guess that would keep you energized, wouldn't it? Yeah. Um, right. Somebody says you've got to rush back home after park run to make it to the masterclass. Yeah, that's it. Or do you just sacrifice one park run to kind of do it? Who knows? And also, you should be finished the park run at like 9:20, surely. If you start the park run at 9, you should be around the course in 20 minutes. If that's kind of, or maybe at least 25 minutes, 30 minutes. So you should be back by 10:30. Yeah. Right. A polythene sheet with a relative permittivity of 2.3 is inserted between the plates so it completely fills the space between them. State what is meant by a dielectric constant of 2.3. So I guess this just means that it has a permittivity that's equal to 2.3 times the permittivity of a vacuum. Yeah. Oh, yeah. By the way, yes, it's a free masterclass tomorrow. So basically, it's £20, but you put that code in and you get £20 back. So it's basically £0. But it's only through my website. It's not a live YouTube live stream like this one over here. Okay. So what do we mean by a dielectric constant? It's basically the I guess the permittivity. I can't remember how to spell permittivity. Is it 1T or is it 2 T's? Let me just double check. So the permittivity is 2 T's. And it's literally spelt out in your equation sheet. The permittivity of the gap is equal to 2.3 times the permittivity of free space. I think that's pretty much it, isn't it? It's in the question. It literally is in the question, isn't it? There's no excuse to get words spelled incorrectly when it's literally there. Thank you so much. Yeah. Cool. Right. When the polythene sheet is inserted, the distance between the plates remains constant and the capacitor, having been disconnected from the battery, remains fully charged. A student correctly states that the capacitance of the capacitor increases. Okay. Why does the capacitance increase? So basically what we do is we start with this and we've got a certain charge Q0 between the plates. If that's disconnected and then we put in this other material that's over here, we still have the same number of charges on each of the plates. So Q0 doesn't change. But of course we do know that Q0 is equal to CV. And what happens to the capacitance? Well, basically the capacitance goes up because the potential difference between the plates goes down. Okay, so that's something that we've got. Basically, we put something else in the middle. We then have a small electric potential between the two plates. So how can we explain that, or how can I explain that? So if we think about, again, I'll just do a quick diagram. Let's imagine we had the two plates of the capacitor. This is got a positive charge, and this one here is a negative charge on it. When you put the polar molecules between it, the polar molecules basically line up like this. So imagine we've got a load of molecules which have a slight charge at one end, and of course the negative end is going to be attracted to the positive, and the positive end is going to be attracted to the negative. So we've basically got these polar molecules lined up in that gap between them. And what this means is now we've got, if we think about it, we've got an electric field going from positive to negative. So there's kind of like a field going this way that's due to the, so basically there's a field going this way, but there's also another kind of counteracting field going in the other direction. So what this is doing is reducing the electric field strength between these two things. Okay, is that right? Yeah. Yeah, so basically it's the electric field is equal to V over D. And of course, by having something that's kind of working against the electric field that was there, that means the electric field is reduced. We've got the same distance between them, and therefore that's why V goes down. And of course, if V goes down for the same value of charge, so Q over V is equal to C, if V is going down, that means C must be going up. Is that right? Cool. So, so basically, the polar molecules reduce the field strength because they align in, I guess, the opposite direction to the field. Or that, I guess they align, yeah, they align opposing the field. Direction. We can therefore say that reduces the potential difference between the plates. And then also we can say that for the same charge, C is equal to Q over V, and therefore the capacitance increases. Yeah, so something like that, basically sort of three kind of big bullet points to help explain that. Is that right? I think that's right. Calculate the difference between the initial energy stored by the capacitor and the energy stored when the polythene has been fully inserted. So, again, always worth looking at the equations. We've got these three ones here that are useful. So the energy is going to be equal to, let's do a half Q squared over C. Okay, so initially, when in the initial state, the capacitance of that capacitor was 330 times 10 to the 6, and the charge stored was 3.96 times 10 to the minus 3. We're going to divide that by 2 times 330 times 10 to the minus 6. So we can work out the initial store of energy. So let me just do that. Is that 6? Is that too nice? Is that right? Oh, did I not square that? Need to square the charge. I got 6. Square Q. Okay, so basically we take that multiplied by 3.96 times 10 to the minus 3. So it should be 0.02376 joules. Okay, so I'm just going to write that all down. So that's the initial energy. Afterwards, the energy is going to be equal to a half Q squared over C. But of course, now we've got something where we've got something with a relative permittivity of 2.3. And of course, that means that the capacitance is going to increase by a factor of 2.3, isn't it? Is that right? So that's going to be the same charge of 3.96 times 10 to the minus 3. So I'm actually going to square this time. And then we're going to multiply that by 2 times 2.3 times 330 times 10 to the minus 6. Which I guess I think that's right, isn't it? So basically, we can do the same thing that we did before. So 3.96 times 10 to the minus 3, square that, divide by 2 times 2.3 times 330 times 10 to the minus 6. And that's equal to 0.01033 joules. And I think that means the difference between these two things, I'll write it in another colour, so the change in energy is therefore equal to 1.3 times 10 to the minus 2 joules. I think that's right, 0.013. Yeah, cool, that's what I got. Oops, yeah, cool. So basically I think I'm on the right tracks. So that's the initial energy. We've now increased the capacitance because we've now got a relative permittivity of 2.3 times. So that's basically this thing here is the new capacitance. So we've increased the capacitance of that, and therefore the change in energy to two significant figures is 1.3 times 10 to the minus 2. Cool. Right, how are we doing? I think we've got one more question, two more questions, and then we've got basically endless multiple questions, endless multiple choice questions. Why is an AC power supply needed for the transformer to operate? Well, basically what we need to have is we need to have an alternating input. That means we're going to have an alternating magnetic field. And when you've got a changing magnetic field, we can then cause or induce an EMF in a conductor in that magnetic field, which will then cause an alternating current in that secondary coil. So yeah, is that right? Yeah, so why does the AC power supply needed? Because a changing magnetic field is created by the changing a changing magnetic field is created by the alternating current, and then it's this changing field induces an EMF in a secondary circuit or a secondary coil. Does that look alright? Let's see what people are saying. By the way, probably if you want to practice your definitions, do put them in the chat. So it induces a magnetic field, which then creates a changing magnetic flux linkage, which as a result induces a current and an EMF in the transformer secondary coil. I think as well here, because we're talking about Faraday's law, where Faraday's law, the way that AQA have it, how do they have it written down? So Faraday's law, the way it's written down here, is that the EMF induced is equal to N delta phi over delta T. Firstly, you induce an EMF, and then secondly, if you've got a complete circuit, that then causes an alternating current. So I think the main thing I just want to kind of stress here is if you're talking about there being a changing magnetic field, you need to say firstly that induces an EMF, which would then cause an alternating current in a complete circuit. Yeah, yeah, cool. Here we go. Big. I reckon this would be a 6 marker. A student constructs two simple identical transformers for a school project. I guess they're not identical if they've got differences, are they though? So they're not identical, they're similar. So one uses a hollow cardboard tube to link the primary and secondary coils. This one uses a solid continuous loop of iron as the core to link the primary and secondary coils. Okay, so the first one, yeah, this is the kind of thing that you cannot ignore. And I think in the last masterclass, I think we discussed this a few times. about if you do have like these kind of big meaty 6 markers, which you're going to get, there's no avoiding it. Don't forget diagrams can help. Sometimes sketch graphs might be useful, there might be some calculations within it, but also you might consider doing these earlier in the exam while you're still relatively fresh, rather than ignoring it and coming back to it at the very end when everybody's a bit tired and a bit stressed and a bit emotional. So maybe sometimes the big 6 markers you can do earlier on in the exam to kind of basically hit them while you're feeling fresh. Anyway, so the first one, we've got a basically the primary coil, and then we've got the secondary coil like this, and you've got a excuse my kind of poor diagram, you've basically got a tube that they're wrapped around. Okay, so that's kind of maybe the first one. The second one, which it says it's identical, but I guess it's going to be more similar, is we'd have a continuous loop of iron, and we've got the primary coil this side, and then we've got the secondary coil on that side. Okay, so I think that's basically, the first one is A, and this is B. So I think even if you just had a diagram there, that's going to really help your explanation. So, you know, I'm not going to write it out because I think I might just explain it for those of you watching at the moment. How many likes are we on, by the way? Have we got up to the magical number? Let me just check. I'm just going to check on my phone and see what it says. So I can basically see these stats if I'm actually kind of viewing the live stream. So if I view my channel, what have we got? 52 people watching, and oh, it's just adverts coming up on my phone at the moment. How many likes have we got? Come on, people, get in there, keep sharing this. Right, so the first one, we're going to have an alternating current here. That alternating current is going to cause a changing magnetic field, and if we think about what the field lines look like, they're basically going to be coming away from this, and they basically look like the field lines that you might get around a bar magnet, and so you look a bit like kind of sort of butterfly wings, a bit like this. But what we can see is a lot of this magnetic field is basically just going off into the air, and there's only going to be a relatively weak magnetic field that's going to be inside the secondary coil. And if you've got a smaller field here, even though it might be a changing magnetic field, we know of course that the EMF induced in that secondary coil is going to be equal to N delta phi over delta T, but phi is equal to BA. And if you've got a very small value of B, that means we're going to have a very small changing value of phi, and therefore we're going to have a small EMF, and therefore a relatively small current, a changing alternating current in that secondary circuit. Now for B, what we're doing here, did we get past 67? Yes, we did. Not again. Here we go. Right. Basically with B, what happens now is the magnetic field, rather than just kind of going everywhere, it would much rather travel through something which is a good conductor of magnetic field lines. Now it's not the same as conducting electricity, but what we're looking at is something with, it's a word that you don't need to know for A level, but it's called reluctance. So you've got resistivity in an electrical circuit, and you've got reluctance in a magnetic kind of sense. So basically the field lines, they go through here and they all get channeled around, and the ones that would have gone out this way basically also go through this. And that means whatever the size of the B field is over here, the magnetic field here is going to be fairly similar over here. And of course we know that from Faraday's law that the EMF is equal to N delta phi over delta T, but now we're going to have a much bigger value of phi because we've got a much bigger and stronger magnetic field through that same area. And so with a bigger changing field, we're going to have a greater EMF, therefore there's going to be a greater current in this second one. And of course the iron core is designed to conduct the magnetic field lines, not necessarily conduct electricity. Ideally, what you want is there to be no current in this, but you want there to be just the magnetic field lines. Of course, this one's going to become warm. Sorry, my phone is beeping. Okay, so basically, why is it that this one gets warm? Well, what there might be is when you've got this magnetic field, this is also going to cause inside this some induced current, and that's going to cause in here these eddy currents. And when you've got the movement of charged particles, just like in our standard electrical circuit, you've got electrons moving around, colliding with the metal lattice. That's going to cause them to vibrate a bit more, so their temperature increases. So because we've got these eddy currents in this solid piece of iron, which is something that we don't want, these will cause a heating effect, and therefore that means not all of the energy transferred in is going to be transferred out. Some of it's going to be dissipated as thermal energy to the surroundings. Right, number 7. How are we all doing? Everybody good? By the way, are people looking forward to next week, or are people like... It'd be interesting because I guess you've had like a relatively gentle start to A-levels. A lot of people only had 1 or 2 exams before half term. Then we've had like this beautiful sunny weather where it's just been too hot to do anything. And of course, I think for a lot of you doing A-levels now, you basically get hit by physics, by maths, by other subjects, and then you've got this kind of solid couple of weeks of work. So, yeah, people are saying they're more looking forward to the masterclass. Thank you. Yeah, so most of your exams are in June. Yeah, so I think a lot of you are going to have a pretty busy couple of weeks. 3 exams in 2 days. Yeah, somebody just wants to get it over with. Somebody's been in bliss all half term, and then you've got 3 exams when you get back. You've got 5 STEM exams. I mean, that is a dream, isn't it? Nice. Physics, chemistry and maths in the span of 2 days. I mean, that is like, that's some people's dream. Yeah. Right. Right, good to see people in the chat here. All right, number 7. Let's just keep going with this. A school lab has a source of americium 241. It's got this activity, alpha decay. It's got that decay constant. Determine the number of radioactive americium nuclei when it was bought. So, and then it says with an appropriate number of significant figures. I would say, looking at the data here, that's going to be 3 significant figures. So our final answer has to be 3 significant figures as well. And don't forget that you can write this down. Okay, so let's think about what equation we can use. I guess for this, the activity is equal to the decay constant times the number of nuclei, and therefore n is equal to A over lambda. Now it says the initial activity is 4.201 becquerels, 4.201 times 10 to the 4 becquerels, so that's the number of decays per second, and it says here that the decay constant is 4.80 by 10 to the minus 11 per second. So we're going to have seconds divided by seconds to the minus 1, so they kind of cancel. Yeah, so let's just do the working out. That's equal to 8.752 by 10 to the 14. So I would say to 3 significant figures, this is 8.75 times 10 to the 14, and there's going to be no units, or that would basically be the number of nuclei present initially. Yeah. Calculate the activity of the source 50 years after it was purchased. Okay, I think this one here is pretty straightforward actually. Again, if you're not sure, you can always go straight to your data sheet and maybe look at equations that might be useful. This one here, we're going to use the equation that says n is equal to n naught e to the minus lambda t. And of course, we know that the activity is proportional to the number of nuclei. So we can also say that the activity is equal to the initial activity times e to the minus lambda t. Okay, so the activity then is going to be the initial value, 4.201 times 10 to the 4, times e to the minus lambda, which is 4.80 times 10 to the minus 11, and the time is going to be 50 years, so that's 50 times 365 times 24 times 3,600. Now, I've not really seen any difference in the answer, basically, between if you use 365 or 365.25 for that extra kind of quarter day. let's just leave it like that for the moment. So we've got minus 4.8 times 10 to the minus 11 times 50 times 365 times 24 times 3,600, and that's equal to that. Okay, so this means the activity then is 3.9 times 10 to the 4 becquerels, I think. Is that the right answer? And I guess for this one, I'm going to give that answer to 2 significant figures, because we've got 2 significant figures for the time, which is just 50 years. Yeah, so good. American UK saying, if the initial activity was given to 4 significant figures, should you give your answer to 4 significant figures as well? Although that's 4 significant figures up here, the thing is we're multiplying it by something initially which had 3 significant figures. So that's why I'm giving this answer to 3 significant figures. And then for this answer, we've got something given to 50 years. And so because we're multiplying this thing here is like the limiting bit of data. So justifiably, 3.9 to 2 significant figures is correct. Hello, Kyle. Great to see you in the chat. Cool. Right. 7.3. Suggest why the actual activity of the source is likely to be greater than your answer to 7.2. Good question, by the way. Somebody says, in the exam, can you write E minus to represent an electron? I would say that that can be useful if you've got it in a diagram, but I do feel that in a question, in the exam, the time that it takes to write out the word electron isn't significant. So I would say, just to make really sure that whoever's marking your work is completely clear about what you mean, I would say in the exam, write down the full word electron when you're talking about something or explaining or discussing or describing. I think that's fine if you're like maybe doing like a nuclear kind of like reaction, for example, but I think electron is much better. Okay, now of course what we've got here is based on something where we look at the activity over time for the americium 241. But of course it does say that this then decays into neptunium. And so although there might be this amount of americium left and the activity is going down, the daughter product, or the not the daughter product, very much the product of that radioactive decay could also be radioactive. So although you might be getting these alpha particles coming off from this, there might also be maybe alpha or beta or gamma coming off from the neptunium. I can't say it. Neptunium. How do I say that? I don't think I've ever really said that word before. Neptunium. Sorry, right. This is why doing a live is so much more difficult than doing like a pre-recorded video where I can get rid of all my ums and ahs. So Neptunium, that doesn't really sound right. Neptunium might also be giving out alpha. Sorry, that should be alpha, shouldn't it? It might also be giving out radiation as well. So basically, there could be other radiation from the decay products. I think is probably the best way of actually kind of stating that. So there could be other radiation emitted from the decay products. Cool. Neptunium. I might just have to say that to myself for the rest of the day. What is meant by the binding energy of a nucleus? Well, if you want to know what the binding energy of a nucleus, all you need to do is you need to look at some of the flashcards on the website. So if you go to AQA, which is, so this is on alevelphysicsonline.com. If you go to the AQA page, you can see at the top of the page it says flashcards. And if you click on that, you will see like a free sample of the flashcards that I've got available. You can then choose your exam board, AQA of course. The topic in this case might be I guess this is more looking at nuclear physics. And then you'll see down here, I'll just zoom in on that a bit more. I've got flashcards for the topic. You can go through them. You can see what the words mean. So what does the word isotope mean? You click on that and it flips over. And of course you can then, like, if you're happy with it, you can just get rid of that card. Mass defect, let's flip that. The difference between the mass of the nucleus and the sum of the masses of the individual nucleons within the nucleus. Is there one for binding energy? Here we go. So this thing here, if you get an exam question on this, there is absolutely no excuse to get it wrong. You must know your definitions, and I've got all of them here. I've got over 500 flashcards for AQA physics. So binding energy is the energy required to separate a nucleus into its individual nucleons. I think that's a pretty good definition that you just need to know. And basically what you can do is you can get a PDF version of this that you can buy in my shop. By the way, go and buy these. They're pretty good, so you can just buy these, and then that means you've got a PDF document of every single one of my sets of flashcards. You can just print them out or just look at them on your phone, or you can also look at the full set of flashcards on my website if you go to the flashcards section from the label on the side over here. And then of course you can see that if you're doing AQA, even if you're doing things like turning points, for example, I've got all of the flashcards for the optional modules as well. Kyle says, energy required to separate a nucleus into its constituent nucleons. Excellent, perfect stuff, good. So we've done that, we saw it on the flashcard. Did you see energy released in mega electron volts for the decay of one americium 241 nucleus? So I think probably it's worth thinking about the change in mass first of all. So the change in mass is going to be equal to the mass that we originally had divided by, taking away the mass of everything afterwards. Somebody say that it is a shameless plug. Yeah, by the way, it is a shameless plug because I'd love you to buy my stuff, mainly because it will help you with your exams and it will give me money, and I quite like earning money. But also I guess this is now like my full-time job, so basically everything you see on Physics Online, it's not funded by some big corporate organisation. There's not some charity giving me lots of money. There's not an exam board doing this, or people having to pay to go to independent school to kind of access my stuff. Basically, loads of stuff is completely free, or like on this YouTube channel, for example. And in order to kind of keep buying Lego, like you see behind me, it is good to actually sort of sell stuff so that people can buy the things to kind of just make them feel a little bit more confident, ready for sort of the whole kind of A-level process. So yeah, right. So the change in mass is going to be the initial mass. So that's 240.9886. Take away the mass of everything we have at the end, which is 236.9815, plus the mass of the alpha particle. And initially we're just going to work in U, so the change in mass in atomic mass units. Right, so let me just work this out. Okay, so the change in mass is equal to 6 times 10 to the minus 3 atomic mass units. Okay, and then of course what we need to do then is convert from the mass into an energy. Now we could use E equals mc squared, but as somebody's just said in the chat, U is equal to 931.5. So it says here in the databook, and this is why it's so important to be completely familiar with the databook, 1 U is equivalent to 931.5 mega electron volts. So all we need to do then is take this kind of conversion factor, times it by 6 times 10 to the minus 3, and that should then give us the equivalent mass in its energy format. So that's equal then to 5.589 mega electron volts, and I think I'm going to say 5.589 is an appropriate answer in this case. The reason being that that's to 7 significant figures. That's to 7 significant figures. that to 5 significant figures, and the conversion factor is given to 4 significant figures. So I reckon 4 significant figures would be an appropriate number for that thing there. Cool. Oh yeah, I've just seen in the chat over here, for the previous question, you mentioned that decay is spontaneous, so the variance in the activity, would that be valid? I think that when you're looking at a large number of things, and I think we had like 10 to the 14 of these atoms here, although there might be some random nature to the decay, because we have such a large number, that random nature is then like statistically insignificant for maybe 1 or 2 things if they decay or they don't. So yeah, there might be a bit of noise in that signal, but I would say that the noise in the kind of the data that we get is going to be insignificant because we have such a large number. And therefore, if there's a random nature of the decay, that's not really accounting for maybe the additional measured activity of that previous sample. Okay. Right. A student concludes that the initial activity of the source and that after 50 years are very close due to the long half-life. Therefore, if the activity change is negligible, the source is safe to handle without precautions after 50 years. Evaluate the student's conclusion. Of course, you can say that there are no stupid questions, but sometimes students are, they say kind of different things. So although there might be not a big change in the activity that it's giving out is still going to be dangerous because, yeah, although the activity change is negligible, the activity is still high. Even after 50 years. So it must be handled in a safe manner. And so this could be making sure that, for example, you're using a set of long tongs to pick it up. Maybe that you don't direct the source at anybody, or you don't put your hand where that source is pointing. All of those things there are kind of valid, okay? Did I not answer 7.4? I think 7.4 was the one where it was a definition that I showed you on the flashcards that I've got. Okay, end of section A. Right, so we now have multiple choice. This is where I'm hoping that all of you can put your answers into the chat. What I do need to do is I've kind of run out of anything to drink, so I'm just going to go and make myself a cup of tea. Finally, it's not so hot that I can't drink a cup of tea. So what I'll be doing is in my special branded mug. Check that out. By the way, has anybody seen their teachers with these at school? I basically gave about 400 of these away to teachers last summer. But has anybody actually seen them? Has anybody seen their teacher using one of these at school, or have they kind of basically taken them home to kind of use in private in their kitchen when they're at home? But yeah, basically, I'm going to get myself a cup of tea. I'll be back in about 2 or 3 minutes. Until then, I'll let you have a look at the first question, try and work out what the answer is, and I'll see you in a couple of minutes' time. If anybody's seen anything, by the way, also, that's another question. Has anybody seen these things here? I gave a load of these out, and I've bought thousands more to give out this summer. So these things here can go into schools, to go on the walls, and maybe I need to work out a better way that these can be sent to people. Those mugs are too special to keep at school. Right, let me know if anybody's actually seen any of my branding that I've sent out. If not, I maybe need to do a better job. Okay, somebody's got them all over the labs. Excellent stuff. Right, I'll be back in a couple of minutes. Okay, right, I'm back. Let's see what people are saying in the chat. Okay, people are talking about, right, some disgusting people out there eating pineapple on a pizza. No chance. Right, do I definitely don't like. I mean, I like pineapple and I like pizza, but together, no, just not right. Okay, so I have asked. I've answered that. Right, can I just ask though? A lot of you have got maths stuff next week. Can you let me know in the chat if you do Edexcel A-level maths? If you do, just say in the chat that you do Edexcel A-level maths. If you can do that now, that'd be amazing. Just to find out of the people watching, whoever's still watching, if that's something you're doing. Because this Saturday, after I'm doing my kind of capacitor workshop in the morning, so that's like an hour-long masterclass from 10 till 11:30, there's also going to be a masterclass in the afternoon aimed at A-level maths. So we've got, is that C-Line? We've got Enki, American, we've got Amrit, oh no, OCR, never mind. Ajan, Hydration, we've got Keeman, Lucas, loads of people. Basically, it seems to be that the most common combination is AQA Physics and Edexcel Maths at A-level. But there's going to be a workshop that's going to get you ready for your exams next week, and that's going to be at 1:30 or from 1:30 till 3:30. It'll be in the same office, and you can book that on my A-level physics website. The person who's doing it is Joe. So what I'm going to do is do a quick video call to Joe, and then what I'll do is I'll put him on the screen. Let me see. I'm ringing him now. We'll see if he actually answers. So the person who's doing that, Joe, can you hear me? I feel, yeah. Have you got your video there?
Do you want me to turn it on?
Yeah. Right. This is Joe at the moment. Say hello to Joe, everybody.
Hello.
Yeah, so some of you might have seen he did a free maths masterclass, I think last weekend, wasn't it?
Yeah, Saturday morning.
Yeah. Actually, this is good, because if I put you here, right, Joe, basically you are now like the Lego man on the screen. That is something that's so cool that I can't really explain how good that is. So basically, right, I'm going to have to send you this afterwards. This is awesome. A lot of people are saying, hi, Joe. Yeah, so basically, do you want to explain what you're doing on Saturday, tomorrow?
Tomorrow, so I'll be doing a revision class for Edexcel A-level Maths Paper 1. So the first bit will just be me explaining the kind of topics that I think students get stuck on or have trouble with, and then things that I think might come up in the exam, as in if they do come up, they would often catch people out. And then it'll be more Q&A near the end. So if anyone has any questions on specific topics, I can answer them. And then on the masterclass on Tuesday, so the day before your paper, that'll be more just Q&A, answering any questions people have. Yeah, whereas tomorrow will be a bit more led by me, and then the end will be Q&As.
Cool. Awesome. Yeah, good. I know you're a bit quiet because basically I think my microphone doesn't always pick up all of the chat. But yeah, basically this is Joe. He's going to be doing a maths masterclass tomorrow and also the night before your actual exam. So you can find everything that you need to know over A-level physics online. And I guess, Joe, if you go into the chat as well later, you might be able to answer questions if you've got time to do that. All right.
Yeah. Any questions, put them in the live chat and I'll answer as many as I can.
Awesome. Right, Joe, you don't understand how good that looks with the Lego figure and your head on it here. Right, Joe, thanks a lot.
All I can see is your camera. Is this what the paper sees?
Yeah, that's what the paper's seeing. Right, everybody.
Your forehead.
Yeah, you just see my forehead, can you? Oh, yeah, there we go. Right, okay, thanks, Joe. Cheers.
All right. See you in a bit.
Okay, how's that? So basically, that's Joe there. He'll be in the chat. That's Joe Catamore Tutoring. So he's got his own tutoring business as well. But he's basically going to be doing stuff. You can book it all through my physics website, A-Level Physics Online. And that means you can book into these maths masterclasses as well. Cool. Right, let's get back to it. So, okay, I haven't actually worked through these questions myself. So I need to work out how to actually approach them. I would say my top tip for anybody doing multiple choice questions is if you think it's going to be difficult, leave it, move on, come back to it later. The other thing is if you see like a numerical thing like this, treat it like any other physics calculation from section A. So just think about what is the equation you're going to be writing down, what is you're working out, and then use that to find the right answer. Lots of people are saying D. Okay, so let's do it. So basically, we've got this much gas. It's a constant pressure. The temperature of the gas increases from 20 to 30. What's the work done? So the work done is equal to the pressure times the change in volume. So that's one of them that you need to know about. So basically, we've got a constant, is that right? So what else do we need to know? Okay, let me have a quick look. Give me a second. We don't know the pressure, but we know the temperature. Oh, okay, so we know that PV is equal to nRT. So that means so P delta V is going to be equal to nRT, nR delta T, is that right? So basically, if you've got the same pressure, the same number of moles of the gas, and you've got the same value of R, delta V is going to be related to delta T. So that means the work done is going to be equal to nR delta T. And of course, N is equal to the number of moles is equal to the mass divided by the molar mass. So that's equal to mR delta T over M. Am I right? Yeah, cool. Yeah, by the way, hello everybody. Joe is in the chat as well. Thank you, Amari. Okay, people are saying it's D. Right, let me just do this. So we've got 8 grams divided by 4 grams per mole times 8.31 times 100. So that's going to be 2 times 8.31 times 100. So that's going to be about 16.62 times 100, which is equal to 1662. There we go. Didn't even need a calculator for that one. Therefore, the answer. Did anybody say it was D in the chat? Did anybody else hear the plane? Yeah, I've got my window open now because it's so hot, and there's a really low plane going over. So hopefully, well, I guess some of you might have heard that. So yeah, the first one is D. Right, number 9. Let's have a look at this. So, a sealed container of gas at constant volume has a pressure of this at a temperature of 27 degrees. The gas is then cooled. Okay, so basically this is very much like the thing where if you have a gas and you cool it down, there's going to be a point where if we're thinking about the temperature of that thing and we've got the pressure up here, there's going to be a point at which the pressure becomes 0 at 0 Kelvin. So at what temperature will the kinetic theory suggest that the pressure of the gas should become 0? So it's going to be down here, which is 0 Kelvin. So it's not that one, and it's not that one. Okay, and what is the physical interpretation? That means that the average kinetic energy of the molecules is 0 because they're not really moving. So they're going to be the point where they have minimal internal energy, and effectively they're not moving anymore. So that's true, better than that statement, and therefore B is the correct answer. So we've got Kyle, Amari, we've got the Melon Doge. Okay, we've got Celine Creed, we've got Kura, we've got Yash. why doesn't anybody? Why do so few people have normal names anymore? Okay, as in like I can't read all of these numbers. Like three. Right. Is this just like randomly generated usernames that a lot of people have? I do like though that when people have their username, Kurapika Physics. I do like. I know you've got a normal name, but it's like the D6F afterwards. So that's what I mean. As in like. Amari Quinn, yeah, I understand you've got a normal name, but it's like just trying to read the username and there's like lots of numbers and stuff after it. We've now got, I guess that's Vish8426 saying B as well. Good stuff. Right, the usernames are taken. That's true. That's true. Okay, right. A fixed mass of an ideal gas has a volume V and a pressure P at a temperature T. The temperature of the gas has increased, so the new RMS speed is doubled and the pressure triples. So, I guess we say that PV is equal to nRT. Quality Steve. Okay, Quality Steve. That is a quality username. Okay. Quality Steve 2008. Okay. I know, it's an anon thing. So, okay, right. T3C Knox. That's the shortest name. But again, it doesn't roll off. It's very difficult to roll. Some of the names just don't roll off the tongue if it's like T3CNOX. Yeah, okay, anyway, I'll get through it. So we got PV equals nRT. And I guess we also know that from, again, looking at the data sheet, let's see what we've got. We've got some thermal physics somewhere. We've also got we've got a half M C RMS squared is equal to 3/2 kT. So the volume of a gas is going to be equal to nRT over P, and the temperature of that is going to be equal to something over here. So the temperature is going to be proportional to C RMS squared, and of course if we've got a fixed mass then they're going to be the same, and that means we can say that the volume is proportional to the temperature over the pressure, so the volume is proportional to C RMS squared over the pressure. Okay, so that's my interpretation there. So so B, okay, sorry, we're just talking about absolutely random stuff, sorry. Yeah, okay, right. So this one here then, V is proportional to C RMS squared over P. Now it says that the new RMS speed is doubled. So that's like the initial thing. The new one is we've got basically 2 times the RMS speed. And we've got the pressure triples, that's over 3P. So that means we can then say that V2 is proportional to 4/3 of C RMS squared over P, and of course this thing over here is equal to the initial pressure, so V2 is equal to 4/3 of V1, and therefore B, as everybody's correctly saying, is the right answer. Okay, 60F, the hexadecimal identifier, is that what it is? 60F, is that hexadecimal? Yeah, could be. Right. Okay. I do quite like hexadecimal numbers, by the way, because I use them quite a lot if you're looking at all the colours of things. So what you'll find is that if you look at like, there's basically hexadecimals are used for the red, the green and the blue component of colours that you use. So I think FF9700 is like the hexadecimal colour code of the orange just beneath me at the moment. I think, or is it? I can't remember what it might be. It's something like that. Okay, number 11. A proton and an electron are separated by a fixed distance in a vacuum. What's the ratio of the electrostatic force to the gravitational force between them? So the electrostatic force is equal to QQ over 4 pi epsilon naught r squared. and that's going to be divided by the gravitational force, which is equal to mm, or gmm, over r squared. And that means we can see that both of these have a thing over r, so they cancel. And then I think all we need to do is put lots of numbers in, because then we've got basically the charge on each. Oh, this one here looks like an easy thing to do, but it takes a lot of time. So we're going to have basically the charge on an electron and a proton. So that's going to be basically 1.6 times 10 to the minus 19 squared. We're going to divide that by 4 times pi times 8.85 times 10 to the minus 12. And of course, we're then going to be dividing all of that by 6.67 times 10 to the minus 11 times 9.11 times 10 to the minus 31 times 1.67 times 10 to the minus 27. Okay, divide by divide, so that's messy, I should have done it better. People are saying D. What do other people think? Is it D? Should we just pretend that's equal to D? I think from memory that is the right answer. I think I've managed to remember all the constants correctly. Yeah, you may not be cooked after all. Yeah, I think from memory it's about 2.3 times 10 to the 39. It's a fairly standard question. I know I've used it in my daily workout books. Pretty sure it's D. Let's just say it's D. So equals, yeah, the answer is D. Good, let's move on. Yeah, it's D, cool. The diagram below shows the gravitational equipotential lines around a planet of mass m. A space probe of mass 150 kilograms is moved from the middle equipotential to the outermost. How much work is done by the gravitational field during this movement? So if it's 150 and that's the potential of joules per kilogram, then the change in gravitational potential is equal to minus 20 joules per kilogram. And that means the change in gravitational potential energy is going to be equal to 20 times 150, which is going to be, what, 3,000 joules? Now, for this one, is it B or C? I guess work is done. I guess if work is being done, that's when there's a force acting over a distance, but this is acting in the other direction, so... Oh, I don't know. B, because you're moving against potential, or is it C? Yeah, so basically it's becoming more positive. So work is done by the gravitational field. Well, if it was doing work, it would be doing it that way. So I think C. Don't know what. I don't know. I'm going to say C, but I don't have work is done by the planet. So we're doing work in the other direction. So I guess that's going to be minus 3,000. Do I ask ChatGPT? Tell you what, I'm gonna do something different. I've used ChatGPT yesterday. It gave me the wrong answer. Let me just take a picture. Okay, so this is using Google. Well, okay, that's the wrong question. Oh, here we go. It's saying the answer is C. So this, let's have a look at this. Right, so let's just do a bit of an AI check, a bit of a sense check. I asked a question yesterday in my stream, and it gave the wrong answer. I asked it, is the piezoelectric effect in OCR physics, and ChatGPT said no. And then I checked the specification and it was there. So it says, identify the change in potential. So we've done that. Calculate the change in potential energy, plus 300. The work done by the field, since the potential energy increases, work was done against the field, and therefore work done by the gravitational field is the negative of the change in its potential energy, so it's going to be minus 3,000. Yeah, answer C according to me. There we go. Oh, I guess, yeah, the change in potential, it goes from 40 to 20, so that's plus 20. So the change in energy is plus 20 times 150. Yeah, there we go. Sorry, that one there. I suspect if this was a real exam question, half the students would get it wrong. Okay, what is... Oh, here we go. Number 13. I guess we're going to assume that's a right angle triangle. Got two stars of these masses. A point x is a distance of 1 times 10 to the 11. What's the magnitude of the resultant gravitational field strength at point x? Well, I guess there's going to be a field here, or there's going to be a gravitational field strength there. And there's also going to be a field which is acting, or a force acting in that direction. And then I guess we then need to work out the resultant of these two things. Oh no, sorry. The gravitational field strength. Yeah, so I guess what we need to do is work out G due to M, this M, and we need to work out the value of G due to that thing as well. Okay, so what's the magnitude of the resultant field strength? So let's look at this one here. G is equal to GMM over R. I suspect if I was doing this in the exam, I would just be moving on because it's quite a lot of calculation, is it? So yeah. Yeah. Okay, so the field strength G, so if we think about, let's call that planet A and planet B. Let's do the field strength due to planet B is equal to GMM over R. So that's going to be 6.67 times... Oh, sorry, it's just GM over R, isn't it? Hold on, have I made that mistake? Is it GM over R squared, isn't it? Sorry. So you've got 6.67 times the mass of this here, and that one's going to be 3.7 times 10 to the 30, divided by the distance between it, which is 1.0 times 10 to the 11. That's going to be squared. And so GB, let me just work this out. So many people are saying A, some people are saying B. Is it just GM over R? So yeah, so basically G is equal to GM over R squared. Okay, so that's going to be the field at a point around a point mass. Okay, yeah, I reckon this one here is too much work for a 1 mark question. And so if this was a real exam question, I know how to do it, but I'd leave it to the very end. So I just look at it, go, that's a lot of work for 1 mark, leave it, come back to it later. Okay, so if we just put the numbers in, so you've got 6.67, said it again, times 10 to the minus 11, times 3.7 times 10 to the 30, divided by 1 times 10 to the 22, is equal to 0.02. Yeah, I did say, yeah, okay. And then, of course, you can do the same for this one over here. Now, of course, if that's one side of a triangle and that's 1, then that side there is going to be equal to 2 squared minus 1 squared. So that's going to be equal to root 3 times 10 to the 11. And therefore, that's going to be, if you're dividing by root 3 times 10 to the 11 squared, that's going to be 3 times 10 squared. So it's basically going to be this answer divided by 3. Is that right? So the other one, so GA, because it's basically root 3 of an additional distance away. If that's 1 and that's root 3, then that's going to be 1 over R squared. So that's going to be 1 over 3. So it's going to be basically a third of that. So that's going to be 0.00823. And then, of course, the resultant of these two things is going to be equal to this squared plus this squared square rooted. which equals 0.026, and therefore B is the right answer. I'd say that's quite a lot of stuff there. So B, I did it. Yeah, there we go. Right, a beam of electrons is fired horizontally into a uniform electric field. Right, so this one here, even though it's a multiple choice question, you should still be starting with a diagram to help your explanation. There's nothing wrong, there's nothing that stops you doing this. So a beam of electrons is fired horizontally into a uniform electric field going vertically downwards. So that's basically the field is doing this, and here we've got a negative particle that's going into that field. What describes the motion of the electrons? So basically the field line points in the direction that a positive thing would move, and that means the negative thing would be moving upwards, and it would be going through a parabolic path like we saw in that previous question. So the force is always going to be in this direction, so we'd have a parabolic path upwards with a constant horizontal velocity. So I think actually A is the correct statement. So B finally, yeah, so A says Bingus 6646. Yeah. Amrit B says A. And also I think a lot of other people are putting A in for that. So they don't continue in a straight line. That's not true. We don't accelerate in a horizontal direction, so that bit there is not true. And they don't have a downwards parabolic path. Okay, there we go. Cool. A says Yash Chavan. Cool. Right then, 15. Oh, here we go. Another one about electric charges and stuff. So a positive charge is moved from point A to point B in a uniform electric field. The electric potential at A is higher than at point B. So maybe here we've got a field, and I guess we might have some kind of equipotential lines going across it. They go from point A to point B, so that's what's moved. The electric potential at A is higher than at B. So what happens to the electric potential? Well, if it's gone from a higher potential to a lower potential, that means the electric potential energy of the thing will have decreased, so it won't have increased or it won't have stayed the same. And the work done by the field is, if it's gone from a higher to a lower, that means the work done by the field is positive. It's like the opposite of that question we had before about the gravitational field. So the work done by the field is positive to move it to that point with a lower energy, and therefore C is the right answer. C, says Selin Creed. Amrit says C. Brandon Wiggins says C as well. Cool. Have we still got like another 16 questions to go? This is just endless, isn't it? Is everybody doing all right? Not too hot this afternoon? I reckon we should be done in about half an hour, so probably about 2 3/4 hours. And hopefully people are watching this, and hopefully as well it's being useful. Let me just check something. One sec. Cool. A capacitor is connected as shown in the circuit below. Pretty straightforward. Which statement correctly describes the initial flow of charge when the switch in the circuit is closed? So once we shut this, so let's imagine that we shut this switch like that. We're now going to have the movement of electrons from the positive plate around here. So we're going to have electrons moving this, electrons are going to be moving this way around, but conventional current is going this way around the circuit. So looking at this, protons flow is an incorrect statement first of all. So that can't be A. Electrons flow from the top plate. Well, they're not, because although we've got conventional current going this way around the circuit, the actual electrons are going to be moving this way around that circuit. So that's definitely not true. And conventional current flows from the bottom plate. That's definitely not true. So this question, although it says it's about a capacitor, it's not really. It's more about when the switch is shut, what happens from the cell if we kind of think about that. And of course, if you've got electrons moving this way, we then have like the negative charge up here, and we'd have a positive charge on the top plate because the electrons would move away and move round to that side. So here, B is the answer. Bingus 6646, correct? Is that right? Oh, sorry. Oh, hold on. Have I made a mistake? So electrons flow from the top plate of the capacitor. Okay, no, that bit's true. Okay, so the electrons are moving this way around. Okay, so that bit is actually true. I'm going to put my corrections in red. While the bottom plate gains electrons from the negative. Okay, that's true. Electrons flow from the negative terminal of the battery to the top plate of the capacitor. Okay, that's not true, is it? Right, people, read the question. So yeah, the answer is C. It's not that one. Okay, thank you, by the way, to American UK comments and viewers when I kind of say the wrong thing. Is that like why people are controversial on social media? Because if you do the normal right thing, people don't really mind. But if you say the wrong thing, people kind of let you know about it. So yeah, basically this one here, read the question. Read the question. Make sure you read it properly before you just jump in with the answer. I didn't read it, and therefore I would have made a mistake in the real exam. Let's move on and pretend that never happened. Okay, a capacitor is discharged through a resistor. This shows the potential difference across a capacitor of time t, so all pretty standard. What's the resistance of the capacitor used in the circuit if the capacitance of the capacitor is 2.5 millifarads? So, make that a poster. I do have a poster of it, actually. 1 second. Actually, I do have a poster about reading the full question, but I don't have it here. Basically, we've got units and significant figures. Don't forget that. No drinking in the lab. That one there is routinely broken by every single science teacher who takes in a cup of tea or coffee into the lab at break time or lunchtime. But I've got these other ones. I've got to read the effing question one, but that one is... I don't have any left to kind of show. They're all in the big box somewhere. Okay. You have the no drinking in the lab. No way. That's awesome. I mean, yeah, probably what I need to do is send a lot more of these out to schools, and probably one of the best ways would be, is it better for me to send it direct to your teachers, or in the future, imagine if you put yourself back in the mindset of like a little year 12 student like you used to be, would you rather be able to request it yourself to give to your teacher, or is it better if I send stuff direct to teachers? Let me know. There might be a way that I can do this. Okay, we'll see. We'll see. Right. What is the resistance of the resistor used in the circuit if the capacitance of the capacitor is 2.5 millifarads? Well, I'm going to look at the equations that we've got here for capacitors. And basically for capacitance, the half-life... Okay, so there's a few things we can use. Basically, one of them is the time constant. So the time constant of a circuit is equal to RC, and the time constant is the time it takes for the potential difference to fall to 1 over E of its original value. And if we think about that, if you do 1 divided by E to the 1 is equal to 2.71, so 1 divided by that is equal to 0.368 of something. So basically, when something falls to 36.8% of its original value, that's the time equal to the time constant. Okay, so if we know that's 6, basically 6.0 multiplied by 0.368 is equal to 2.2. So what we can then do is, looking at this graph, that's going to be 2.2. I'm just going to use my ruler to draw onto the graph what that is. This looks to me to be about, it's a bit hard to tell to be honest, but I reckon it's about 3 seconds. So basically that means the time constant is equal to 3.0 seconds. And of course we know that the time constant is equal to RC. So R is equal to T over C. So that's 3.0 divided by the capacitance of 2.5 times 10 to the minus 3. And I guess that's going to be about, we can do this in our head actually, because that's going to be 3 over 2.5 is like 6 over 5. So that's about 1.2. And then it's 10 to the minus 3, so it's 1.2 kilo ohms. So 3 divided by 2.5 times 10 to the minus 3 is equal to 1200. So that's 1.2 kilo ohms as the resistance. Yeah, so when something is equal to 0.69, so basically 0.69, no, sorry, wrong number, right, I've got that number in my head now. Basically, if you look at the natural log of 2, that's 0.69, and effectively the half-life, I'm going to call this, let's call that T a half, is equal to RC times the natural log of 2, and the natural log of 2 is 0.69. So basically the time it takes for something to fall to half of its original value, so going from V down to 3, this is basically the time it takes here is equal to RC times the natural log of 2, whereas the time it takes to fall to 37% of its original value is equal to RC. Okay, is that all right? Cool. I'll do more about this. I've got a free capacitor masterclass on Saturday morning at 10:30. So you'll either be seeing this beforehand, where you can book onto it, or you'll be seeing this afterwards, in which case I did a masterclass on Saturday morning. But if you're watching this before Sunday, I do have a paper 2 masterclass Sunday afternoon. Okay. Right, an oscilloscope is used to display an AC voltage. It's initially showed, there's basically too much text here. This one here, lots to do for 1 mark, so maybe leave it and move on to it later. Okay, so just as you have a read of that, let me know what you think the answer is. Okay, so it basically says, it's got initially 2 complete cycles, and we want it to show 2 complete cycles again, but now we've got a frequency which is 4 times higher. So initially the time base is 4 millivolts per division, sorry, 4 milliseconds per division, but now if we've got something where the frequency goes up by 4, that means the time period needs to go down by a factor of 4, and it needs to go from 4.0 down to 1.0. So it has to be one of those, because we've increased the frequency by a factor of 4, so the time base has to go down by a factor of 4. Yeah, this is a horrible question maybe. The peak voltage is 2 vertical divisions above the centre line when it's 1 volt. But now the peak voltage goes down, is half of the original signal. So that means this needs to go from, okay, so the peak voltage, when the Y gain is set to 1 volt per division, but now if we halve the voltage, that means we need to double, that means we also then, so the peak voltage is a half of the original value, so that means we need to use half the value of this to get the right signal now. So we go from 1 to half of that, which is 0.5. So it's not 0.2, so the answer is A. Yeah, that one there, not a nice question. Yeah, I would say that many words and stuff, skip it. Yeah. A resistor then dissipates thermal energy at an average of 40 watts when connected to a sinusoidal AC power supply. So let's draw this out. So initially, we've got a power supply that kind of looks like this. Okay, it's got a peak voltage of V0, as expected. If it had been connected to a DC power supply with a constant voltage of V0 over root 2, what's the average power dissipated? Well, basically, the RMS value is kind of like a value a bit like that. And effectively, if you've got something, imagine you had, a peak voltage of let's imagine you had a peak value of potential difference equal to 10 volts in an AC supply. Okay, although it might go up to 10 and down to 10, this isn't the same as a 10 volt DC supply, because that's always 10, whereas that one gets to 10 and then it becomes less than 10 and then up to 10 and then less than 10. And so basically these two things are not the same. In actual fact, the 10 volt AC supply is going to be the same as a 10 volt DC supply divided by root 2. So that's going to be 10 over 1.41 is the same as a 7.07 volt DC supply. Okay, so that's kind of what we mean by the root mean square speed. It's kind of a better indication of the actual power that's being transmitted. And so if the same resistor is connected to a DC power supply with a constant voltage of this, then actually that, whatever that is going to be the same as this. And so the power dissipated is going to be the same. So it was 40 and it continues to be 40, but now we've got a lower constant value of potential difference in this second circuit, and therefore C is the right answer. Okay, does that make sense? Yes, Chavan, 3221, C, excellent stuff. So yeah, the answer is C. So basically we've got a lower voltage in a DC circuit, but it provides the same power as a much higher voltage that's alternating in the first circuit. Okay, right, this one here, this could be nice. I quite like these ones. Don't look at those until the very end because they can get a bit confusing. It says a proton of mass m is accelerated from rest through a PDV before entering a magnetic field. Okay, so we know that the charge on the proton is E, so the charge times the potential difference is going to be equal to the kinetic energy of that particle in that field, and therefore we can use that as one of the equations. The other thing that we might remember is that from looking at the motion of a charged particle in a magnetic field, the force it experiences, BeV, is equal to mv squared over r. So we're going to use these two things here. Yeah, I reckon this is a nice question. So one of the v's cancels, and therefore we can say that BE is equal to mv over r. And we're trying to find the value of B. So B is equal to mv over ER. So that's the first thing we can say. The second thing is we can use this thing here to find out what the value of V is. So that means V is equal to 2EV over M square rooted. And we can basically put this into there to say that B is equal to M over ER times the square root of 2EV over M. Now that at the moment is the right answer, but it's not any of those. So what we've got is an M times root M, and there's a E, or 1 over E times that. So I think, I think for this one, what I'm going to do to make it easier for me is I'm going to say that B squared is equal to M squared over E squared R squared times 2EV over M. And I can then see we've got M squared over M, so they cancel. And then we've got E over E squared, so they cancel. So we can say that B squared is equal to 2V, like M2V over ER squared. And that then means that B is equal to the square root of m2v over er squared. And I guess you've got a square root of 1 over r squared. So looking at what we've got over here, it's still none of those. Therefore, that's equal to 1 over r times the square root of 2mv over e, which is a. Is that the right answer? Yeah, there's probably easier ways to do that, because I guess that's just root m times root m if it's just m. I guess I just did this the other way just to kind of make sure I didn't make any mistakes. Quite a lot of working out there. Is that the right answer, people? I've got some answers here actually. I haven't actually checked. Yeah, I think I'm correct. Cool. Right. So my phone is just beeping. I'm just going to see who this is. Cool, right. A stationary positive charge is placed in a uniform magnetic field directed vertically upwards. Okay, so for this one, a stationary positive charge, it's in a magnetic field going up. So that's the magnetic field. And then we can use Fleming's left-hand rule. Okay, the magnetic force. Right, so the first finger is the direction of the field. The second finger is the direction of conventional current, which is moving charges. But this thing, it says it's stationary, and so there's no moving charge, so we can't use Fleming's left-hand rule. And basically that means there's going to be no force in it. So you only have the force, which is equal to BQV, when you've got something which is moving, but of course V is equal to 0, so that means the force on it is 0, and therefore D is the right answer. Yeah, there we go, there we go. How's everybody doing? Is anybody still watching? It's a long... Has anybody been here from the very beginning? It would be amazing if anybody's actually had me on in the background for a couple of hours. Has anybody been here from the start? Well, we'll see. Right, number 22. Okay, this is a kind of confusing thing. So, a current carrying wire placed in a uniform magnetic field produced by... Okay, here we go. So we've got a current going that... We've got a current and we've got a magnetic field. No way. Okay, so Amrit, Kyle, Ajathan, Rollis, okay, hydration. Okay, there's quite a lot of people there. Hydration 332. How on earth did you get that name? That's a strange one. Okay. Soothing Tone says T3CNOX. Okay, hopefully relax. Yeah, Skill got you that name. Fair enough. Good answer. Okay, right. So, which statement describes how the reading on the scale changes and the physical law responsible? So, first of all, let's think about what's going on. So, we've got the first finger for the field, which is going north to south. The second finger is going to be conventional current, which is going that way. So, there's going to be a force down on the wire. And of course, if there's a force down on the wire, that means by Newton's third law, there's going to be an equal and opposite force in the other direction, which is acting on the magnet. So basically, the magnet is going to have a force acting upwards. It's basically going to be lifting up, so the reading's going to decrease. So actually, the reading decreases is correct. The reading increases is incorrect. And the physical law responsible is Newton's third law, because basically, although there's a force on the wire down due to this is going to cause the force on the magnet up due to the wire. So it's a pair of Newton's forces. So A is the correct answer. So I think 22, the answer is A. Am I right? A, I think, says somebody. Yeah, cool. Right, there's a lot of bits of paper on my floor at the moment. A bar magnet is pushed north pole first into a coil of wire connected to a sensitive ammeter. Okay, so a bar magnet, so we've got the magnet here. That's north and that's south end. And this is going into a coil of wire, so it's going in that way. And of course, as it goes in, it's basically going to have a changing magnetic field next to a conductor. So we're going to induce an EMF, which will then cause a current in this, and that current will be opposing the change that caused it. And if you've got a current here, we can use the right hand grasping rule to basically look at the direction of where the north end of that would be. And what we'd actually find is that if we were to think about the field lines within this, so we'd have these kind of sort of field lines like this, the north end of that field would be here and the south end would be there. So you'd have the north end of the magnetic field in that solenoid would be opposing the north that's coming in. And so the coil is going to repel the magnet, so that's true, so it doesn't attract it. And that's due to the force is basically going to be opposing the change that caused it, which is due to Lenz's law. So I think probably B is the best of those answers. Okay, yes, Chavan, Flower Journal, lovely name there. Both of you saying B correct. Yeah, these adverts, I mean, to be honest, again, you've got to think about it. There's going to be PMT need money to run what they do. They need money to pay the people who've actually written the question. And I guess the reason they're giving this away completely for free is that there'll be some people buying into the PMT courses and stuff like that. And ultimately, that's how they generate revenue to keep doing all the good stuff that PMT do. Just like, I guess I'm doing this free masterclass or this free live stream to try and convince you to come along on Sunday to pay for the extra stuff that you get. So yeah, there we go. Such a service. Yeah. But of course, you know, you don't have to pay. You don't have to go on the PMT courses to still benefit from this. Okay, a simple AC generator produces an alternating voltage with a frequency F and a peak voltage V0. Okay, so this is, let me draw it on another piece of paper. So imagine this is what we initially see. If you double the frequency of rotation, we know that the EMF is going to be equal to N delta phi over delta T. And if we're making something move twice as quickly, that means the time for one cycle is going to halve. So T is now a half of what it was, and therefore the EMF induced is going to increase by a factor of 2. So what we'd see would be basically something like this. Sorry, that's an awful... Oh, that is absolutely awful, isn't it? Basically, we'd have twice the frequency and twice the height. So the frequency doubles, the peak voltage doubles, and therefore 24, the answer is A. Okay. Number 25, there's a special cheat thing here that you can use, which isn't given to you in the data book, but I have seen it in another thing. So the EMF, or the electromotive force, is equal to BLV. So this one here is an equation that's not given to you in AQA, but it's something that can be useful. And ultimately, if you're panicking, if you've got a couple of minutes left, the best thing to do is if you see some numbers and you want to know what the answer is, just multiply them all together and you might be correct. So here the EMF is equal to the flux density 0.60, times it by the length 0.25, times it by the velocity of 4.0. And of course, a quarter of 4 is just 1, so you've got 1 times 0.6, so the EMF is equal to 0.60 volts. So here the answer is C. So this one here is something that they don't give you, but if you want to look at the EMF of a moving conductor in a magnetic field, B times L times V. Not sure, just multiply all the numbers together and you might well be correct. Okay, I think we've got about 6 questions to go. Cool, so I think we should be done by 5 o'clock. Okay. Okay. A step-down transformer is used to power a low-voltage device. Okay, there's a lot going on here. What's the average current flowing through the primary coil? So with a transformer that's 80% efficient, the power in times the efficiency is equal to the power out. And this symbol here just represents the efficiency. Do we know, okay, the connected device draws a power of 60 watts. So we know power out, so that's POUT. And we know the efficiency, so we can work out power in. So the power in is going to be equal to 60 divided by 0.80, which is 75 watts. And also, we know that P is equal to IV, and therefore the current is equal to the power over the potential difference, which is 75 over 230, which equals 0.33, and therefore the answer is D. Cool. That one there, relatively straightforward. Just try and identify anything like this. Okay. We've got an alpha particle. Okay, this is standard. This is a standard question. An alpha particle with a certain kinetic energy is going to be approaching something until all of that kinetic energy is transferred to electrostatic potential energy. So that kinetic energy is going to be equal to the potential energy. And therefore we can say that this is equal to the potential energy between two charges. Let me just double check that. Is equal to where is it? Well, the electric potential is this, and therefore we just need to multiply that by the charge, and therefore that's equal to QQ over 4 pi epsilon naught R. Okay, and we're trying to find R, so therefore R is equal to QQ over 4 pi epsilon naught times the kinetic energy, and the charge on one of them is going to be 79 times the elementary charge, and the other charge is going to be an alpha particle that's got a charge of 2e, and so you've got 2 times 79 times e squared, so that's going to be 158 e squared over, hold on, is it any of them? Is it any of them? Is it B? Oh yeah, 79 over 2 is the same as 158 over 4. So that's 79 over 2 times e squared over pi epsilon naught ke. Yeah, so there you go, my mistake. Therefore the answer is B. Thank you very much, Kyle. The chess player, great name. Celine Creed, and also Yas Chavan, all of you getting B, perfect. Yeah, this calculator is a Casio. I'll just zoom in a bit. It might be a bit blurry, but basically this is just a Casio FX991EX class whiz. And all I did for the setup was basically shift setup, and then I went to input output number 1, and I went to, I think, number 3, so line input, line output, so that's number 3. And that's why I get it on 2 lines, which works really well. And I think that it's a basic calculator, but it basically does everything you need for A-level physics. Come on then, 4 questions to go. Let's do it in 14 minutes. A nucleus of carbon-12 has a radius RC. An unknown nucleus has a radius that's twice the radius of that. What's the most likely nucleon number? So I always forget the way that AQA give this equation, because it's slightly different to the way that OCR did it. So basically R is equal to r naught a to a third, and that means r over a to a third is going to be a constant. So if we think about the carbon, first of all, and then we think about the unknown nucleus over the atomic number of the unknown to a third. Okay, so basically these two numbers, these ratios are going to be the same. So we can say that this radius, okay, so we can say that basically the radius of the carbon is 1 over 12 to the third, and that's going to be the same as this unknown nucleus that's got twice the radius divided by this number a to a third, and therefore this number to a third is equal to 2 over 12 to a third, or the cube root of that. So okay, it's definitely not one of my answers here. I think I made a mistake in my calculator. Does this live stream save after it's finished? Yes, George, James, it does. Yeah, right. Okay, so basically we can do this, and then that's what we find then. Sorry. Have I done that right? Oh no, that's not right, is it? Yeah, basically when you do this, it's 96. Sorry. Just having a moment there. I think I've been doing too much of a live today. Which row do you use in AQA? The number, they'd probably give it to you in the question. It's sort of, there's numbers that I've seen between sort of 1.2 to 1.5 femtometers. There's not just one number that I've seen, but often what you can do is basically, in this one here, you didn't need to know it, because basically, you know, the constant r naught is equal to r over a to a third, and therefore you can then work it out without actually having to know what answer they'd use there. Okay, so that's the answer for r naught. Says R for Matt. Cool. An unstable nucleus decays by beta minus to form a metastable state with a daughter nucleus which subsequently decays by gamma decay. Which statement about that process is correct? Okay, the part beta minus and the gamma are emitted at the same time. No, because that would happen first, followed by the gamma, so that's not true. The emission of the gamma causes the proton number to decrease. Well, that's not true, because it just, you have the same number of protons left afterwards. The gamma ray has a discrete energy equal to the difference in energy between the metastable state and the ground state. That's actually true. And of course, when you get gamma given out, the nucleon number changes. That's not true, so therefore C is the right answer. Cool, Kyle, excellent stuff getting the answer for C. 3 more questions to go. Okay, a nucleus X has a proton number of 70 and a neutron number of 105. So let's find this on the graph. So we're going to go up 70 here. So let me just do that really precisely. And then the other number is 105. That's probably a bit harder to do. But I reckon it's something like that. What type of decay is nucleus X most likely to undergo? I reckon looking at this appears to be on that stable line there, and therefore if it's one of these stable nuclides, then it's got the right number of protons and neutrons, but potentially it could be, like in that previous question, something which is like meta-unstable, so like technetium-99m, where it's got this kind of energetic, the nucleus is in like a higher energy state than it wants to be, so it'd be emitting a gamma photon. So I think that D would be the right answer. What we tend to find is that things which are up here on this is called basically the NZ chart. So you've got N over there and you've got Z on the bottom. So this thing is called the NZ chart. Up here, when you've got lots of things in the nucleus, that's where we tend to get alpha decay. When you've got stuff down here, we've got beta decay. Now basically stuff down here on this side of the line is going to be proton rich, and there's going to be more protons than neutrons, and that means what happens is a proton decays into a beta plus and a neutron. So on the bottom side over here we get beta plus decay, and on the top side we tend to get beta minus decay, and that's where one of the neutrons becomes a proton, and basically the thing kind of moves down here. So whatever's here moves this way. On this side, whatever decay does that. And I guess over here, if you give out 2 protons and 2 neutrons, you get a movement like that. Now, I would say, looking at this, the answer is B. It could be B. It's definitely not alpha, and it's unlikely to be beta. But you see, I guess on here, looking at the line, it looks to be on that line of stability where you've actually got a dark nuclei which is stable. So I guess it could have just the right number of protons and neutrons, but it might just be in a metastable state. So I guess if it was on the stable line, so for example, if we picked this one over here, so let's just zoom in. If we picked this one over here, that's on that darker line, it's kind of on the line of stability, so it's unlikely to go beta minus or beta plus because it's already on that line of stability. If it's just above the stability line, I think if it was above, then it could be the answer B. But I think looking at if it's on the line of stability, then it's probably going to be that. But I think it really depends on, and they wouldn't ask you the same question with a graph of this scale because you can't tell exactly. Yeah. Yeah, I think that's my answer. What does it say on the PMT thing? You can tell it's not alpha because it's only normally really heavy things that give out alpha, as they basically try and sort of they basically have just too much stuff in the middle of that nucleus. They eject 2 protons and 2 neutrons to have a lighter nucleus. And that's why it's not alpha. So basically on this NZ chart, beta plus down here, beta minus up there, and alpha up there. Okay, yeah. What's the actual answer say? Okay, the PMT answer they've given us is beta, but I don't really agree with that so well. I think that maybe gamma would be a better answer based on that thing. Okay, oh my god, the last page. 5 minutes to go. In a nuclear reactor, a chain reaction is sustained by the fission of uranium-235. What does the moderator do? Well, the moderator moderates the speed of the neutrons which are emitted to make them thermal or slow neutrons. So it doesn't absorb them. That's what the control rods do. To absorb thermal energy produced by the fission reaction. No, fission reaction. That's what the coolant is doing. To slow down the fast neutrons, yes. And that's kind of some kind of cladding around the edge. So the answer is going to be C. Nice. Quality Steve, Yash Chavan, both of you saying C. Good. Yeah, excellent. Celine Creed. Yeah, cool. Nuclear fusion is the process by which 2 light atomic nuclei combine to form a single heavier nucleus, releasing a large amount of energy. What condition is essential? Easy. So I've not even read this. So I guess this is going to happen at high pressures and high temperatures. You need a high pressure, so there's a high chance of a collision, and a high temperature, so that things have got enough kinetic energy to overcome that electrostatic repulsion before the strong force takes over. So I reckon that's not true. That's true. That's not true. That's not true. The answer is B. There we go. End of the paper. Yes, Chavan, excellent stuff. So there we go. That was the PMT predicted paper. Like I've always said, these questions, I don't think they are accurate predictions of what exactly is going to come up, but they are the kind of questions that kind of are, I reckon, to be fair, some good standard physics questions that you need to be aware of, and also the approach to actually answering questions in the future. So yeah, yay, congrats, Aura, mic drop, perfect timing. Yeah, so basically, I think I've done enough for the day. I'm going to be back again tomorrow in the same office where I basically feel like I'm living at the moment. 10:30, I'm going to be doing a capacitor masterclass. If you want to book it, head over to alevelphysicsonline.com, look at the booking page. Then you can get £20 off the capacitor class if you use the code capacitor20. Then in the afternoon, there's a Maths Edexcel A-level Maths Edexcel class that you can book again on my website. That's from 1:30 till 3:30 with Joe. Then on Sunday, I'm doing an OCR masterclass at 10:30, AQA masterclass at 1:30, Edexcel masterclass at 4:30. So please come along. I'm going to be here anyway, so it'd be great to have as many people there as possible. Monday, I'm doing a GCSE live stream before paper 1 for the little GCSE kids. Tuesday night, there's going to be an Edexcel masterclass and so on. So yeah, lots and lots of stuff happening. But yeah, good to see everybody there. Let's do another paper. No chance. Yeah. Yeah, cool. Right, if I had to do a physics paper every other week for some random people, I'd lose it. Yeah, okay, right. And hopefully as well, just helping with your confidence. I think by this point, you know what you're doing. You're going to be absolutely fine. And I'm sure, by this stage, you know it now. You're going to be absolutely fine. And I hope it all goes really well next week.